So thank you very much. Hello, everybody. I am Franklin Kenghagho from the Institute for Artificial Intelligence in Bremen, at University of Bremen, led by Professor Michael Bate. So thank you again for the opportunity to yeah, share our work on traceable semantic train for enabling reasoning in complex scene. So this is what I will be sharing with you in the next 25 minutes. Okay, next.
Sorry.
So before I actually tell you or show you how we enable reasoning in complex scene through the digital twin technology, I would like first to illustrate the reasoning problem here. So as you can see on your right, so there's a human actually performing the sterility test, and this sterility test process require a lot of information about the context to be executed. And when you see the history of robotics, the distributions of process basically lie on the domain of pick and place tasks, where once you know about the pose of object, you can basically perform the process. But when it comes to real world, it becomes insufficient to just know about the pose of object. Thank you, Marcus, for this brilliant work about the detections and pose estimations of transparent object. But more than that, we need to know, for example, how objects behave or how they behave when you interact with them during the process executions. For example, when you see the robot on the right part of the screen trying to manipulate also as the human, there are a number of questions that the robot has to answer before actually successfully perform this sterility test. Let's say that you know the pose of the transparent object, the bottle, for example, that the robot is holding or grasping. Another question is, once the robot release this bottle, many things can happen. We can reach like a different situation. One of those situations, the situations where the bottle fall and get broken and you lose the, let's say, sample of fluids, which can be really damaging for the whole systems. So we see that to actually manipulate, we don't just need, let's say, the pose of object. And another question, for example, is how firm the robot should grasp the bottle so that it doesn't get broken. If you're, let's say, picking stone, no matter how hard you pick or you grasp them, there will be no kinds of danger or problem. But once we have like a breakable object such as bottle, you should be also careful about how hard you or how firm you actually grasp the bottle. So this type of question should be answered by the robot. And there are also cases or situations where the robot has absolutely no kinds of sensor data about the world. For example, imagine that this bottle kinds of roll and fall out of the table. So given the field, the view field of the robot camera, it will not be possible to have like images of this bottle. So the robot will be completely lost. So the question is, how do we man or human actually solve these types of problem in, let's say, situations where we are lacking sensor, where we need a lot of information about the physical dynamics of object to be able to successfully manipulate them. So this being said, we go to the next slide. Yeah, so it comes out that long time ago an answer was provided to this question, but only at the psychological level, not at the robotics level. And these are mental simulations. So Hislo already long time ago work on the fact that human heavily rely on the mental simulations to provide this generative mind, this mind which is able to anticipate what is going to happen when you interact with, let's say, object. We all know that, oh, if I place this bottle in a certain configuration, it will fall somehow. The question is, how do we know such type of things? It comes out that this mental simulation. So mental simulations here are somehow mental executions of real world. So you need a very cool model of the real world to be able to knows in detail how it will work, even if you don't have a sensor data about the world. So his role elaborated on this mental simulation as a solution to these kinds of reasoning problem. But the premier is it did not tell us how to actually realize those mental simulation. So our scientific contributions regarding this is not only to bring this psychological insight into the robotics realm, but to also somehow provide an answer to the question of the representation. And it comes out that the representation here is a digital twin of the world. So a digital twin is a physical realistic replications of the world, as you can see on the screen. So on the left side, you see a real robot, and on the right side, you will see, let's say, the digital twin, which is somehow a physical realistic. So it is photorealistic and it's also physics faithful. And giving this representation, we are able, as I will show you, to answer those questions regarding the, let's say, the parameter of actions and the effect of action to be able to successfully and safely execute such complex processes. Okay, next. Yeah, so this is now, for example, one of the first feature of the semantic digital twin. So here you can see that we are able, let's say, for complex action to replicate what the real robot is doing. So we synchronize these representations with the real world. So this means that even if we are out of our sensor data, let's say the camera, we are able to know where the canister is because we are emulating the actions of the real robot, and there is no a priori limitation to the process that we can actually emulate. As I will show you also at the end how we are going further and further. For example, here you can see that we don't have a tube, but it is under kinds of work, and we will also show you how we deal, for example, with fluid. Okay, next. So the semantic digital twin is not just, let's say, this sub-symbolic representation as you have been seeing. We also know all about, let's say, that world, because everything in that world, so object and interactions, are grounded into, let's say, an ontology, and we kinds of build also our own ontology, the Zoma ontology, which kinds of model the context, the physical context and the social context of the world. So the physical context here, for example, is the objective world. So, for example, that a bottle is transparent is like an objective kind of descriptions of the bottle. But you can see that bottle on the one hand as a container, depending on how you interact with that bottle. So we model such types of knowledge to be able also to reason depending on the context and solve problem. So giving this union of, let's say, symbolic description of the world and sub-symbolic description of the world, we somehow have a two-roof kind of knowledge base to actually parameterize action and control. For example, I can say what force, for example, should I apply on the bottle so that I successfully grasp it, giving the weight without it slipping as though out of the grip or getting broken. You can answer this type of question. Or how should I release the bottle so that it doesn't fall, it stay kind of in a standing position. Yeah. So in the next, so the next things regarding the traceable semantic twin is the traceability. Um, um, Here what we are doing is we don't just have, like, the traceable semantic twin is not a black box, so we know everything that is going on from the beginning of the process till the end, and we can export all this and replay it for many reasons. So one thing is like a post execution kinds of investigation. So someone want to know, for example, how everything's happened during the process execution. And if you want to perform, for example, things like actions verification, the cause of an action failure can go back to the beginning of the process. So to actually explain this failure, you also need to know what happened at the beginning of the process. So here we have a format for extracting or for exporting the semantic of the execution, and we call this a narrative enabled episodic memory. And here we show to you that we can export the whole robot execution. So as you can see on the right of the screen, we have exported, for example, a specific executions into the web browser. And these are different kinds of environment. For example, here the simulation is going on in the ARVIS that you might know, and we were doing, let's say, this, or we build this semantic digital twin using Unreal Engine, which is like a kind of physical realistic game engine. So if we can actually map the semantic between those two kinds of game engine, it actually means that we have the structure of that process. So if you go to the next slide, you will see that if you go to the next slide, you will see that we could, during the process, extract all the semantic and be able to replay them. So here, for example, we don't have like a camera sensor, but we are able to replay the whole process because we have, let's say, this trajectory of object, the data about the robot motion and the interaction between the robot and the object. So you can use this later as a review of the robot execution. You can use this, for example, for further experiment. You can use this, for example, for verifying what happened during the process. Okay, next. So now we come, let's say, to another feature of the TST. We saw how we can actually maintain a very cool belief of the robot, how we can export the robot execution. Now let's see how the TST provide action verification and failure recovery. For example, here we demonstrate how you can use this TST to recover from failure. We know that, okay, a failure happened, we can actually kind of execute the, let's say, the actions in the simulation and actually get, let's say, the execution that actually succeed and replay it in the on the real robot. So if you go down, I will illustrate these different actions verification. So the first action verification is the physics based. So we basically rely on physics law to verify. Here, for example, we are looking for, let's say, this sequence of motion and parameters that will lead to the successful insertion of the canister into the drain tray. We try many and parameterize, and we get the simulations, and we get the parameter of the simulations that actually succeeded, and we use this for the real robot execution. And here, for example, you have seen, if you play this again, you will see that if you jump at the end, so here is where we try to estimate the parameter, the right parameter and motion sequence. So here you see that the perceptions can be, let's say, wrong or inaccurate about, let's say, the height or the pose of the object. And when you try to imagine, so those detections in the semantic digital twin, you realize that there's a discrepancy between the reality and the detection from the traditional perception. And this is how the physics in the semantic digital twin will correct the pose of the object. And this pose will then be used back by the perceptions module. Okay, next. Next, Anthony. So we don't just have we don't just exploit the physics in the semantic digital twin. You also have what we call imagistic kinds of base reasoning here. So the question is, if you actually have a mind's eye or an imaginations of how the success should be, then you should be able, after the executions of, let's say, the process, to compare, let's say, what you see and what should be. So given this technology of semantic digital twin, we are able, for example, as you can see on the left of the screen, here is, for example, the robot trying to insert the red cap into the canister. So it's a very tiny object, and it could be very difficult to check whether or not it was successful. So this is how we use this technology to verify such type of things. So when the robot is executing, we also emulate the robot. So, and after the insertion, we kinds of have mentally the region where the cap is in the world. And we try to compare that region, so the sensory images from that region and the sensory image from that region, but from the real images. So we have the mental images, we get the region where the cap is located in our mental image, and we also get the region where the cap is on the real image, and we compare both of them. As you can see on the video, so here we have the situations. This is the real image. We want to check if it was successfully inserted. We imagine, let's say, a successful insertion, and we compare the region where the cap are, and they are successful. Here is a failure because we have like this discrepancy between those images, and we conclude that it was unsuccessfully inserted. So next. So the next category of verification is what we call contact-based verification. So this is another great advantage of the digital twin. The thing is, we have a very explicit and thorough collision model of the environment. So we don't need a sensor or whatsoever. We can detect any collision between the robot and any part of the environment because we have the complete kinds of scene in our mental world. So for example, here is what is contact based. We try to perceive event based on contact. On the left, for example, you will see that most of the time when you place a container full or half full, it usually vibrates and it will ultimately fail or fall or stand or skip or stay in a standing position. So based on the contact between the object and the environment, you might be able to infer the state of this object. For example, imagine that the robot placed the canister under the table. So, and you, based on the semantic digital twin, realize that there is like a collision and there is like a support and non-support state sequence. There is like a sequence of support and non-support of the placed object. So according to the ontology, this corresponds to what we call a vibration. So it means that the object that you place is somehow unstable. So this is how, based on contact from the semantic digital twin, we can also verify action. Okay, next. So for example, here is the example of a collision detection from the semantic digital twin. So we are able to know that when the robot was trying to place the object into the drain tray, it kinds of collide with the pump. Okay, next. So now we have seen how we can export the whole robot execution. We have seen how we can do kinds of recovery. We have seen how we can verify actions. So at the end of the process, we generate kinds of a concise documentation of the executed process. These documentations tell you exactly what happened, when, by what component, which object were involved, what was the result of the verification of this action, what was the confidence, and it gives you also explanation, so verbal explanation and non-verbal explanation. For example, here non-verbal explanation will give you the precise images when the robot actually performed that action. So we are able to tell you, okay, when the robot inserted a canister into the drain tray, that was the image of the scene, and you are able also to directly see that it was successful. And we call this document an audit trail. Okay, next. So we have said that The digital twin technology is somehow the emulations of the real world, the simulations of the real world. We have seen how we simulate robot action. We have seen how we simulate object kinds of dynamics. But we also have a human, and we can also emulate human action. And in this case of TraceBot, for example, we show to you how we can let the robot, a human, teach the robot. How does it work? So the human actually perform an action. So it tells the robot how to actually perform the sterility test. Let's say here the case of the canister insertion into the drain tray. Then what the robot does is it observes the human. Can you play the video? Yeah, so it observed the robot observed the human, and it tries to extract, let's say, post information from the human and reconstruct this scene into the semantic digital twin. And once he has done this, he gains insight about the action parameter, for example, how to grasp an object and so on. So the question here is, robot and human might have like a different kinematics. How do you then how do you then ensure that the parameter that you got from the human will be useful for the robot? So this will be the next slide. So in the next slide, we show to you how we map actually those parameters from the human to the robot. So this is an example. The technology here is basically to determine or to define key point between human and robot kinematics and try to minimize, let's say, the gap between both uh, sequence of key points. Okay, next. So then I tell to you here, or I kind of tell the story a bit of future work. We have like a fluid simulation. Here, the point is, if you're also able to emulate the dynamic of the fluid, then you will be able to perceive the fluid even without sensor. So, for example, here we have a transparent object. Imagine then that your bottle is not transparent. So you don't have, for example, the possibility to see, for example, the fill level. How do you then overcome this type of things? So the answer is, if you go to the next slide and play, we show to you how we are able to build, let's say, reliable physical model of the fluid and also emulate the real robot manipulating the fluid in order to infer, let's say, the state of the fluid. Here we have a robot pouring, for example, the rice into something. It doesn't have any information about the content of that blue cup, but we can see that if we emulate actually the real robot, it will be able to infer that, oh, I'm still having some things in the cup and so on. And we try to mix, let's say, Navier-Stokes model of fluid with physics informed neural network with simulation in order to build such types of model as it is shown here. So here you basically see that we observe, let's say, a real fluid. We don't need a lot of sensor data about this demonstration. We just need, for example, how long it took a human to pour a certain fluid from one container to another using a certain motion. And using this, we are able to infer the parameter of that fluid and construct, let's say, a reliable physical model of the fluid and emulate the robot manipulation of fluid. Okay. Okay, next. So this is a bit a demonstration about what the fluid looks like and so on. So the next thing is uncertainty in simulation. Simulation is good, but you can only rely on simulations if you also have the right parameter, right? So for example, let's say you want to grasp this canister. If in the simulation we don't have the right friction of the canister surface, you will not be able to rely on the grasping from the simulation. So what we do is we infer the parameter of the real world based on what we call a filtering of simulations particle. So what we say is at the beginning we don't just have one simulations, but we have a probabilistic distributions of simulations that are represented by a set of sample that we call particle, if you're familiar with particle filter. And then we filter the most likely particle over time based on the evidence that we have. So next, so in this video, we basically shows a bit how it works. So it's just a short demonstration. So here we have a, a robot, for example, that is facing a situations where we have these four objects in front of him, but we are uncertain about the exact positions of those objects. The robot maintain not only one simulation, but a probability distribution of simulation. And over time, it will filter the best particle and keep them. So those particles that are kept actually carry the right parameter of the real world. Okay, next. So yeah, so finally, to close this presentations, all what I've presented can be translated as a scene understanding, where we model the scene and the activities performed in the scene as a situated hidden Markov process with decision, as you can see. And so what we do is we basically try to emulate what the world is, but we don't just keep one emulation, but multiple emulation because of uncertainty, and we filter, let's say, the best emulation over time based on the evidence that we have. Um, so this is the mathematics behind the work, and in the next slide are the list of publication if you're interested in more about yeah the work. Thank you very much for your attention.
Yes, thank you. Thank you, Franklin. Any questions regarding this this presentation? I hope you meanwhile have a real better understanding what we mean by verification and by combining digital twin with sensing and how this all works together. But I see no hand, I see no question. Any comment from anybody else? Otherwise, Mathieu is already prepared to handle a start.
Well, I can make a quick question just to animate a bit, and thank you, Franklin, for your presentation, and to respect the time, which is something that can be noticed. With the work of one of your colleagues, where we use a real video to deduce, the manipulation that is performed, and then we can transmit that system. So you were using a model of PR2. Do you think that we could, in a close future, to use this type of technology to present to the system a video recording? So first, do we need is it 2D image or 3D image? And so that then we can use that and have it executed by the robot side. So how much, is it, are you far from there, or is it getting nearby?
Yeah, so today we are at the level of a prototype, so close to interpretations of our I could put, let's say, more videos regarding the demonstration here, but we are at a level where we are already able to let the robot pour something from one container to another by observing just the human pouring. So it is already like a workable prototype, so something which is at a very usable stage. And regarding the question about the input, we are using solely RGB images without the depth. So if you go back to what we do is we use RGB image because you will only rarely see images or videos on the web with, let's say, depth images. So we only base on RGB images. So you will see that in the middle there's a mesh. So this is a very strong kind of prior about the world. So we already knows how a human looks like, and we will only need a few things about the RGB images to be able to produce a very workable mesh in the simulation. So this is something that is what to be mentioned, the mesh in the middle, the very generic mesh in the middle. So this is the very generic kinds of mesh of the humans and so on. So we use this as a prior to actually and avoid, for example, if because we are using a neural network to actually extract information about the key point on the human, we cannot deal with inconsistency here because we are forced to rely on this prior mesh of what a human is. So if we get, for example, two articulations on the human, let's say, arm, then we remove, let's say, one because we know that the human arm may be, let's say, we have this wrist and so on. So we remove all what is inconsistent.
Okay.
I just see that Joris asked the question. It's about the combination of force feedback and vision. So Joris asks for the example, if you have a plastic bottle today, some are very thin, some are not so thin. So obviously you cannot determine the difference by vision, or this would be the expectation. But can we, within TraceBot, determine or distinguish between the thinner and the not so thin bottle by combining vision and force feedback? And perhaps Mathieu, you can also that, because I mean you are the specialist on force feedback. Or Franklin or Markus, anybody in the call who wants to take this question, you see it in the list of questions.
Yeah. So regarding force feedback, as I say, we are pushing the limit of these semantic twins more and more. Here, for example, a lot of people doing a bit this work rely on what we call attachment. Attachment is when you want to grasp some things in the digital twin, you basically algorithmically attach the object to the robot creeper. But in this demonstration, we are not doing this. What we're doing is we really try to implement those physics in the engine, things like the friction and so on, so that if I say that the canister has a certain friction and I try to grasp it in the simulation in a certain manner, I will get quite a similar effect as I was if I was in the real world somehow. And the same thing is also about this force feedback. I show you, for example, how we are kinds of modeling a fluid based on scientific model of fluid in Navier-Stokes one. We are also kinds of implementing tactile things in the digital twin to be able to have, let's say, uh, the modeling of soft object and solid object in a way that if you press an object within the digital twin, if it is well parameterized, you will get almost the same effect as in the real world. And because you don't just have like one simulation, you have a multiple simulation with different parameter, you will be able to note at the end that, oh, there is a simulation that produce an effect similar to what we have in the real world. So it means that this object in the real world is a soft object.